Welcome to Python Pro by CRESCENT Technocrats. This is day 21 where we will dive into data structures and algorithms. Uh, I guess there are no interviews without DSA. So DSA plays a vital role in any field of software engineering. As you might think by now, DSA is basically problem solving. Right, let's start with the basics. What exactly are data structure and algorithms? We can think of data structures as the different ways we can organize and store data in our programs. It's like choosing the right tool for the right job. We wouldn't be drinking our soup with our fork and eating our noodles with our spoon, right? Now let's talk about algorithms. An algorithm is like a recipe, a set of steps to solve a particular problem or to perform a specific task. So to understand data structures and algorithms, we can think of this example. For example, to build a house, we will be having the raw materials such as sand, bricks, steel, bars. On top of it, you will add the building instructions to get a finished product. It is the home. In the same way, data is just all the raw materials. They are raw processed data where we will be applying algorithms to get a finished product, the software applications. As we saw, the definitions of data structures and algorithms is here. Now moving on to complexities. There are two types of complexities when running or executing a program file. Those are time complexity and space complexity. These complexities are a measure of how running time or space grows as the input size of the program grows. Here are big O notations. Big O is basically a metric used to describe the efficiency of the algorithms. Let's see an analogy here to get the deeper understanding of the whole concept. Let's say you are trying to transfer some data from one place to other. Think of two methods here. One is transferring the data through electronic means, and the next one is physical transfer of the data, meaning you are going to transfer it in person. So you might think transferring the data by physical means is an inferior way. But let's see. If we are going to transfer some megabytes or even some gigabits of data, you can use WhatsApp, you can email, or you can use any other form of electronic transfer. But if we are going to transfer some terabytes of data, it won't be as simple as while we are dealing with gigabits of data, right? Because terabytes of data might even take days to transfer. So it will be best to transfer the whole data in person. As you would see, the amount of time required to transfer data through electronic means grows and it depends on the amount of data we are dealing with. But in physical transfer, the amount of data never affects the time of transfer. For example, if you are going to transfer 1 megabyte of data or even 1 terabyte of data, it will take the same amount of time. So this is how basically Big O works. Let's say we have two files, code 1 and code 2. They are written in a different way, but they both provide the exact functionality. So files providing same functionality can be measured with just a stopwatch. We can start a stopwatch, run it, then note the timings as readings and stuff. But what if we run this? What if one code is ran in a old computer and the other one is ran in a brand new computer? We can't just compare those two, right? But what we can do here, we can compare the number of operations both take. So if code 1 is taking 10 operations and code 2 is taking 12 operations, it will take the same number of operations in any computer, right? The code 1 will always take 10 operations to complete executing in any computer. Same goes for code 2. So time complexity is comparing the number of operations of the execution. On to asymptotic notations, which are Big O. It is also called as Omicron, but it is, we can just say Big O for this. Omega and theta. Big O is the worst case scenario of the algorithm. Omega is the best case scenario, while theta is the average case scenario. Okay, let's see an example to understand the whole concept. So let's say you are buying a car and you have to find the mileage of it. When you are trying to find the mileage of it, the mileage depends on various conditions, right? For example, the mileage will be higher when you are driving through highway, but the mileage will be much less when you are trying to drive the car in city traffic, and it will meet in kind of the middle when you're driving in both highway and in city traffic. Likewise, big O, the worst case scenario is the highest or the maximum amount of time taken to run an algorithm, while the omega is the best time taken to run the algorithm, while theta is the average time taken to run the algorithm. While we are talking about big O, it is always the worst case scenario. So to understand the whole concept, let's see an example here. So here is an array numbering from 1 to 8. So if you are trying to find one in the array, number one in the array, it will take much less time because it's in the starting. But if you are trying to find the number 8, we have to iterate through 1, 2, 3, 4, and so on till we reach the number 8. So it is the worst case scenario of this array. But what if we are trying to find the number 4? It is just a 3 iterations away and 4 iterations lesser than the worst case scenario. So that makes this the average case scenario. Talk about different runtimes in Big O. There is order of 1 constant runtime, order of n linear runtime, order of log n logarithmic runtime, order of n square quadratic runtime, order of 2 power n exponential runtime, and so on and so. So uh, let's see O of 1, that is constant runtime. Constant time basically means that it is not dependent on the amount of input it receives. Whatever the amount of input it receives, the amount of time going to be taken will be constant. Let's see this example. So I have printed this out here. So what will be the output if the input is 10? It will be 20, because the number of operations always stays 1 in this function, right? Whatever we do, if we give 10, it is not going to be run 10 times, it will be just added only once. What if I give addition of 1000? It won't take much time compared to 10, right? It will take probably the same time because the number of operations for different inputs stays exactly the same. Let's see linear runtime O of n, where we are going to iterate through an array and print the elements of the array. So while we are trying to iterate through the array, the amount of input, the size of the array affects the time taken to get the output, right? If the number of elements in the array is just 2, let's say it will be here. But what if the amount of elements in the array is 5? It will probably be here. But what if it's 100? It will probably be here, right? So linear function is where the input size will affect the time taken linearly. Let's see order of n square runtime, that is quadratic runtime. This is just like linear runtime, but we will have nested loops here. If it is only one loop, it will be a linear time complexity. For example, here we have got one for loop which is of time complexity O of n, which is inside another for loop which is also of time complexity of n, which is like multiplying n into n resulting in n square. That is what exactly happening here. So let's say we have to find the index of the number 78 in the array here. We can use the basic formal loop and iterate through every element, but it will take 8 iteration to get to the number 78. Then it will return the index of the number 78. it will be of O of n, but we can use a much more efficient way here, which is called binary search. So what we can do is, the binary search will basically go for the middle element of the whole array. So it is 36 here. It is 36, so it will compare 36 to the target element, which is 78. As we can clearly see here, 36 is a smaller element than the number 78. So what it will do, it will abandon the whole array behind the number 36, meaning it will cut the array in half. So the size of the input becomes from n to n by 2 here. Why it is cutting it is in half? Cause we can never find the number 78 behind 36, right? Cause the elements behind 36 will be smaller than the number 36. So it can never be larger than 78. So it will cut the array in half. Then we will be left with the next half of an array. So it will again go for the middle element, here 63. So 63 is again smaller than 78. So it will again cut the array in half. So 48 and 63 will be ruled out. We will be left with 78 and 94. The middle element will be 78. And of course, we have found the target element, and it will return the index of the target element. So what happened here? Here in the first iteration, before any iterations, the size of the input was n. In the first iteration, it was n by 2. In the second iteration, it was n by 2 by 2. So it is n square, n by 2 square. And in the third iteration, as you can see, it was n by 2 cube. So we can take the flow of execution and come to the conclusion as kth iteration is n by 2 power k. So we are going to take 1 as k because it is the worst case scenario. So as we can see, we can take 2 power k to this side. So n is equal to 2 power k. We can apply logarithm on both sides. It will result in log base 2 of n equal to k. It will result in log base 2 2 power k. But as in logarithmic functions, we can take the k here in front, and log base 2 into 2 will be 1. So we will be resulting in k equal to log n. Thus, we have a really good efficient manner to find the index of the number 78, which is log n, resulting in logarithmic runtime. So here is a graph of comparison of the runtimes I have just saw. As you can see, O of n lies in the excellent region, then O of log n lies in the good region, then O of n in fair, then O of n log n. O of n log n is basically a log n algorithm contained inside a linear function. For example, binary search inside a for loop will be resulting in n log n. Then O of n square is quadratic, 2 power n exponential, then n factorial is factorial runtime. Thank you.